So thank you for this chance to tell you about our research on diamond magnetometry. And I'm going to describe how we built a fiber-coupled diamond magnetometer and how we want to use it for magnetocardiography and finding corrosion in steel. Magnetocardiography, that's a medical technique where you detect the tiny magnetic fields that come from the patient's heart, and that's known to be useful for diagnosing heart disease and other cardiac problems. Also, I'll tell you how we've adapted our magnetometer so that we can find damage in steel. And corrosion in steel is an enormous global problem, costing hundreds of billions of dollars every year. And our whole approach is based on this fiber coupling, which gives us a sensor head that we can move around and is mobile, and we can put it really up close to the thing that we want to detect. But the fiber coupling means that we can still get good sensitivity by having the rest of our bulky equipment a bit further away. So let me thank the people who've contributed to all this. So this is Raj Patel here. He's finishing up his PhD on this work, and he's really been very central to everything I'll talk about today. Also, Ray Zhu has led on the stuff to do with finding damage in steel. We're very grateful to Element 6, who've provided us with beautiful diamonds that are really excellent for this. Carbon-12, isotopically purified carbon-12 diamonds with nice color centers in them. And we've been lucky to work with companies and with nice funding agencies who've been supporting us on this journey. And here we are at a trade show showing off our equipment. So this is the sensor head. It's quite small here. It's fiber coupled here through a 10-meter fiber to a rack of equipment that's hidden here. And let me tell you more about it now. So here's a photo of the kind of diamonds that we use. We don't use them in this shape. We use cuboids at the moment, but this is a 1 millimeter diamond. Now it's not see-through, it's not transparent. You're used to seeing transparent diamonds, of course, for jewelry. But this one has got this red color that's coming from color centers, defects, nitrogen vacancy defects that we've put in there. And what you can see here is that we're sending in green laser light here from the right. And these these color centers are fluorescing. They're giving off this nice red fluorescence light. And that's what we collect. So we collect this red light, and that's our signal. The amount of red light tells us the magnetic field. But let me describe that in a minute. So this is the structure of these color centers, these nitrogen vacancy centers. There's a vacancy is a missing carbon atom, and then that's next to this nitrogen atom forming this NV center, which has the great properties that we're taking advantage of here. And this is this defect, like I said, it fluoresces red when we shine in this green light. And in order to do some magnetometry, we take advantage of this optically detected magnetic resonance technique. That means that we're measuring here, we're measuring basically the fluorescence intensity, the amount of the red light coming off. And on the x-axis, we're changing the frequency of some microwaves that we're sending in. This is around 3 gigahertz microwaves we're sending in. And these resonances, these features, are due to magnetic resonance of the electron spin of the nitrogen vacancy center. And the optical detection means, it has a couple of big benefits that I'll explain now. So these are the energy levels of this defect in diamond. This sits within the band gap of diamond. And down here, you can see that there's an electron spin of 1 with these 3 possible states. And at room temperature, the system could be in any of these 3 states. But then we send in green light, and that excites the system up to here, and then it decays back, emitting red light. This is this red fluorescence that we're measuring. Fine, so that's how things start off. But now we're going to, like I said, send in these microwaves and flip the spin. We do magnetic resonance and flip this electron spin. And then when we go again with the green lights, the system now is more likely to come over into these dark states. And when it does that, when the system goes over here, then it's not emitting red light. And so there's less red light that we detect. And then a bit later, after a few hundred nanoseconds, the system decays back to this ground state. And the whole system here is very advantageous for us, because just by sending in the green light, we can polarize the electron spin to the 0 state, which greatly increases our signal. And also the measurement of the red light, is this readout technique for finding out the spin state, because we get more red light when the spin is in the 0 state, the spin 0 state. So that's this optically detected magnetic resonance background information. But here now I'm showing how we can use it to measure magnetic fields, because in 0 magnetic field here, then there's a resonance at about 2.9 gigahertz. But then as the magnetic field changes, then these energy levels, the plus 1 and the minus 1 energy levels of the spin in the ground state, they split because of Zeeman splitting. And so then in some magnetic field here, then we see 2 resonances, and they get more and more split apart as we increase the magnetic field. And so this is the basis for this magnetometry, this optical magnetometry I'm going to describe now. This is some background on the literature. This is some of the papers that have gone before. So 15 picotesla per root hertz was the best magnetic field sensitivity back in 2016. And this paper described how you could use a frequency lock so that you were able to have a high dynamic range. That means that you can measure a very wide range of magnetic fields, but still have high sensitivity. This recent paper is exciting. Takes the sensitivity down to even just under 1 picotesla per root hertz using these magnetic flux concentrators. So that's great. But all this stuff is not fiber coupled. These are sort of more like lab experiments, I would say, that are not really designed for applications. So like I said, with fiber coupling, then you get a sensor head that you can put onto the thing you're trying to study, and that's much more practical. And so there's these 2 archive papers that have come out really recently, and then there's and there are others as well. There's lots of interest now in this fiber coupling modality. Okay, and let's get on to what we've done. So this is the rack that we use for our experiment. This is some free space optics in here. There's a lot of empty space here in the rack. And if I play the film, you can see here, this is our sensor head, and we get a signal due to the small magnets that we get in mobile phones. So this is our fiber coupled sensor head that we can move around, and we want to put that somewhere useful to measure the magnetic field that we care about. So doing that, we got down, so in this paper, which was published last year, from Raj Patel et al., we got down, so in the paper we described 300 picotesla per root hertz, and here in our latest data then we've got down to 100 picotesla per root hertz, and here's the noise spectrum. So we're particularly interested in this frequency band between about 10 and 200 hertz. So this is, you know, we're looking for magnetic fields that are varying on this time scale, and you can see that you know, we have this this great magnetic sensitivity. It's 100 picotesla per root hertz is slightly less good than the 35 picotesla per root hertz that's only just come on the archive recently. But we see plenty of opportunities to improve this and to take it down to 1 picotesla per root hertz or lower. Here's a photo of Raj again with a Nobel laureate, just to just because he was the first author on this paper. Here's a schematic of how we built it. So this is the diamond that's doing the sensing. We have a bias magnet, which greatly improves the sensitivity of this whole technique. And we start off, let's start off here with a green laser. We fire that in through this optic fiber, like I mentioned. The red fluorescence then comes back along the same fiber. We detect it on a photodiode. We actually use a balance detector to subtract some of the laser noise. We also have other tricks that are described in the paper, but we have lots of small tricks that each win us a little bit, and that's, I'd say, how we get to this this great sensitivity. It's all described in the paper. So we use a lock-in amplifier because we are sending in these microwaves to the diamond, and we modulate the microwave frequency. We do frequency modulation on there, and that lets us use a lock-in amplifier to reject all the noise that's at a different frequency to our modulation frequency. And that's the basic schematic. And then the concept, of course, is to put this next to somebody's chest to look for the tiny magnetic fields that come from your heart beating. That can be 10 to 100 picotesla, the size of that magnetic field when you're looking on the chest. And so yeah, that's a work in progress. And getting to this sensitivity of 100 picotesla, you know, we were optimizing the things like the microwave power, the you know, the modulation frequency, and working very hard to collect as much of the red fluorescence as possible. But there's loads of great steps to improve this, like the magnetic flux concentrator and going to a gradiometer setup where we have 2 diamonds and we subtract off the common mode noise. So let's go on to the steel scanning. So like I mentioned, we'd like to be able to put our magnetometer sensor head next to some steel and look for corrosion. And so we had a go at that. And the trick to make it work is to include this small magnet here, which is also shown here. So at first we were looking for damage in steel and couldn't find anything with our sensitive magnetometer. And then the great idea came from you know, working with Ray and Raj, and the great idea was to put a small magnet here. This is a tiny little 1 millimeter neodymium magnet, and you would never normally think to do that because that tends to make the sensitivity of your magnetometer worse. So here's the diamond, and this is the bias magnetic field that we normally use. And we like a nice big bias magnet here far away, which gives us nice homogeneous magnetic field over the diamond, so that all of the NB centers are seeing the same field. And then that gives us nice sharp resonances in the optically detected magnetic resonance spectrum, and that greatly improves our sensitivity. And so putting this small inhomogeneous magnet in here disturbs that and makes our sensitivity worse, but it greatly enables us to actually see damage in steel. And you can understand that here, this is a COMSOL simulation of what's going on. And here you can see the steel, and there's a little bit cut away here. That's the the damage that we're trying to image. And this is the big bias magnet here. And this tiny magnet here is the little 1 millimeter magnet here. And this is a zoom, and you can just about see, hopefully on my screen, that there's this bit of damage here. And here's the magnetic flux lines from the small magnet. And basically, these flux lines from the small magnet, they get perturbed by this damage. So they, these flux lines are perturbed by the steel, and then the missing bit of steel provides, an extra perturbation to the flux lines, and then the diamond magnetometer detects that perturbation, and that's how we can do some imaging. So here's an example of this imaging. We had we deliberately made some damage into steel. This is where it was. It had a gradient depth, so it was deeper here. This sample had a gradient in the width, so it was getting narrower at this end. And we scan around, we scan the sensor head around with respect to the steel, and we can see these, we can image this, and then we can compare that here with simulations. The red is a COMSOL simulation. All of these, in all these 4 panels here, then the red is COMSOL simulations that are backing up our measurements and showing that we can really image the shape and the size of what we're looking for. And here's this paper from Ray and Raj et al. And we've got a video here showing it in action. So this is actually speeded up by times 20. So this whole process currently is a bit slow, to be practical, but we can really see how to speed this up and turn this into a useful technology. So what you're seeing here is this is our sensor head, and we're scanning a piece of steel underneath this diamond magnetometer. We're mapping out this damage that we've put in, and we've got no shielding here. We've got no magnetic shielding. We've got no magnetic compensation coils. So things like this are really, I think, necessary for doing this kind of doing this kind of work in the field in real applications, because we want to find damage in steel without having to provide some magnetic shielding or some magnetic compensation coils. Similarly, for the heart, for the magnetocardiography, then people have already done great stuff in hospitals showing that you can diagnose heart disease, but a lot of that work required magnetic shielding and magnetic compensation coils, and so what's needed now is to take these technologies and make them more practical for real applications. So, talking of applications, here's a list of some of the ones that we have in mind. So, this medical one that I mentioned, this also includes MEG, magnetoencephalography, which is a little bit more difficult, I think. But the MCG, magnetocardiography, I really think is going to be a good early application. Non-destructive testing is this steel corrosion application that I talked about. Also, you can try and look for people who've got some steel on them in order to spot people moving around. You can do navigation with a magnetometer if you've got a magnetic map to compare to. You can find unexploded bombs, which is a problem that people worry about in oceans. And some of the features of this sensor are that we can have a small sensor head, has a very high dynamic range. We can work in the Earth's field without shielding. We don't need any cryogens or any vacuum. Solid state tends to make things rugged, and vector magnetometry has been demonstrated. Okay, coming to the end, coming to my conclusions. So I've shown you that we've got to 100 picotesla per root hertz with our fiber-coupled diamond magnetometer, and I showed you that we could find some damage in steel by adding in a small bias magnet. So I'd be happy to take any questions, and thanks for listening.